Hey everyone, and welcome. So, have you ever found yourself trying to process a just massive amount of data, only to watch your system grind to a total halt? If that sounds familiar, you are in exactly the right place. Today, we're diving into one of Go's most powerful and honestly most elegant solutions, the pipeline pattern. We're going to build a high-performance data system basically from scratch, and you'll see just how simple and awesome it can be. So let's start with the problem we're all trying to solve. You've got this fire hose of data. If you handle it sequentially, step 1 has to finish completely, then step 2 can start, then step 3, you're leaving a ton of performance on the table. It is a massive bottleneck, and in the world of big data, bottlenecks are the absolute enemy. There has to be a better way, right?
Well, to figure this out, let's step away from code for just a second and think about a factory assembly line. You've got all these different stations, right? One station cuts metal, the next one welds a part, the one after that paints it. The real key here is that they are all working at the same time, just on different parts. So while one car is getting its final inspection, another is getting painted, and a fresh piece of metal is just starting its journey. That's how you get maximum throughput.
And this, right here, is the perfect analogy for our software. On the left, you've got that slow, one-at-a-time sequential process. But on the right, that's the pipeline. All our steps are running concurrently, just like our factory stations. Each one is busy processing a different piece of data as it flows through the system. I mean, this isn't just a little bit faster. It's a completely different and way more efficient way of thinking about data flow.
This brings us to the formal definition, the pipeline pattern. So what is it? It's a chain of stages. Each stage is running concurrently in its very own Goroutine. And the glue that holds it all together? Channels. Data flows in one direction, through these channels, getting transformed at each and every step. This isn't just a neat trick, it's the absolute backbone of data engineering in Go. Okay, so that all sounds great in theory, right? But how do we actually build one of these stages? Well, it turns out there's a universal blueprint, a simple set of 6 rules that every single stage in our pipeline is going to follow. If you can master these rules, you've pretty much mastered the entire pattern.
And here they are. Seriously, this is a screenshot moment. This is the cheat sheet for building perfect pipelines. Every single stage follows this pattern. It takes an input channel, it creates its own output channel, it immediately launches a Goroutine to do the work, it uses a for-range loop to pull data in, and this is absolutely crucial. It closes its output channel when it's all done. This cycle is the little engine that makes the whole thing go.
Let's just zoom in on rule number 5 for a second, because the for-range loop over a channel is the secret sauce here. It is the magic ingredient. This one little loop does 3 amazing things for us automatically. It blocks when there's no data, just waiting patiently. It receives the data as soon as it arrives, and it automatically and cleanly exits the loop as soon as that channel is closed. It's just so incredibly elegant.
All right, enough theory. Let's get our hands dirty. We're going to build a real, working pipeline using these exact rules. It'll be a simple 3-stage pipeline, but you'll see this template come to life. So, stage 1, the generator. Every assembly line has to start somewhere, right? This is it. The generator doesn't take an input channel. Instead, it just creates our initial stream of data. It kicks things off by sending a sequence of integers out onto a brand new channel.
Next up, stage 2, the power stage. Think of this as our first worker on the line. Its job is simple. It grabs each number as it comes in from the generator, it squares that number, and then it immediately puts the new result onto its own output channel, passing it down the line. It's fast, simple, and runs all on its own.
And finally, at the end of the line, we have stage 3, the sum stage. This is our aggregator. Its job is to collect all the finished products. It consumes all those squared numbers coming from the power stage, adds them all up into a running total, and then, only when the stream is completely finished, it sends one single final sum out.
Okay, so we've built our 3 independent stages. They're like 3 separate Lego bricks. Now, for the best part, how do we click them all together? This is where the beautiful design of Go's channels and functions really shines. Just look at that. It's a single, beautiful, elegant line of code. Because each stage function returns a channel, we can just compose them like nested function calls. Generator creates the first channel, which gets fed right into power. The output channel from power gets fed right into sum. It's incredibly readable, it's clean, and it's doing all this work concurrently under the hood. This, right here, is the beauty of Go.
But hang on a second. This brings up a pretty important question. How does the whole thing know when to stop? We didn't write any complex shutdown logic or signaling. Well, the secret is something I like to call the termination cascade. And the best way to think about it is like a chain of dominoes.
Here's how that domino effect works. When the very first stage, our generator, is done sending all its numbers, it does its one last job. It closes its output channel. That's the first domino falling. The for-range loop in the power stage immediately detects that close, so it exits its own loop, and then it closes its output channel. Domino number 2. That, in turn, signals the sum stage to finish up. It's this perfect, clean shutdown that just propagates all the way down the pipeline. No complex coordination needed at all.
Now, this whole beautiful system hinges on that one tiny detail from Rule 6. So this brings us to a really important cautionary tale. What happens if you forget? What if a stage never, ever closes its output channel?
Well, what you get is a Goroutine leak. The next Goroutine in the chain will be stuck in its for-range loop forever, just waiting for a value that is never going to arrive. It becomes a zombie, silently consuming memory and resources until your application eventually crashes. Honestly, this is one of the most common bugs for people new to Go concurrency, and it all comes down to just remembering to close that channel.
Okay, let's wrap this all up with a little design wisdom that'll help make your pipelines really robust and safe, and then we'll take a quick peek at what comes next.
Here's a huge piece of advice. Try to design your stages as pure functions. That just means they don't have weird side effects. Given the same input, they always produce the same output. Now, why does this matter so much? Well, it makes them incredibly easy to test all by themselves. You can reorder them and compose them however you want, and best of all, you can run them in parallel without ever having to worry about those nasty data race conditions.
And, if this whole pattern feels kind of familiar, it really should. It's the exact same concept as the Unix pipe, which has been around for decades. When you type a command like that, each program is like a Goroutine, and that little pipe symbol, the pi, is the channel connecting them. Go just brought this incredibly powerful, time-tested idea right into the language itself.
So this leaves us with one final provocative thought. Our assembly line is awesome, but what if the paint station is just 10 times slower than all the others? The whole line is going to back up behind it. How do you add more painters, more workers to just that one station? Well, that's where we move beyond a simple pipeline and into another powerful concurrency pattern called the worker pool. But that's a topic for our next explainer. Thanks for joining me.